So we have we have started continuous time Fourier transform last time. Keep in mind that Fourier transform is mainly transforming between time and frequency. And they are true even for non-periodic signal. Does not mean that they does not apply to periodic signal. They also apply to periodic signal. So periodic signal and non-periodic signal, we can use Fourier transform. So we're starting from a claim that we have a periodic signal, which we already know the Fourier series, and then assuming that the period is infinite. When period is infinite, which means frequency spacing is very, very small, and make this the second one in figure B the periodic signal when period is infinite. That means only the center one left, other thing go to infinite, which we cannot see it. Therefore, I'm sorry, I'm losing my voice these days. So therefore, we can consider a periodic signal, which is non-periodic signal X, can be considered to be periodic signal has infinite period. Based on this claim, we put Fourier series representation like that, and then calculate what happens when t, the period, go to infinite. Based on those one, we have derived Fourier series representation, which is this one may be more common form. I think ej omega equals minus infinite to infinite xt e minus j omega t. That's why I see it. In reverse form, which is xt equals 1 divided by 2 pi minus infinite to infinite, like that. Here's minus, here's plus. And keep in mind that this is changing from time to frequency. This is changing from frequency to time. So we have both ways, equation for both ways. Now we are studying how to understand about this. In Fourier transform, we can view as two things. First of all, we can view them as they have complex exponential times some amplitude. So we can think them as complex exponential times the amplitude of it. And also, we can think them as, in case of a periodic signal x tilde, its Fourier series coefficient is equal to equally spaced samples of Fourier transform of one period of x tilde. You cannot get what is the point of it. So let's go back to the story that we have used before. So in here, do you remember this graph? We have used this graph, say that, okay, TAK is our envelope, the basic whole signal, this line. And Fourier series coefficient, we have considered them. Remember that in here, omega equals k omega 0, something like this. So in here, we have TAK, which is the whole signal. And then in Fourier series coefficient, to get Fourier series coefficient, we pick up samples. We pick up samples when k equals 0, k equals 1, k equals 2, k equals 3, k equals minus 1. So we are picking up samples at each k. And then we calculate Fourier series coefficient. And then we make this spacing infinitely small to find this TAK, which is the whole signal. That's Fourier transform. There was Fourier transform. So Fourier transform, we can consider them of this one. And let's reverse our thinking. Let's reverse what we thought. Previously, we're starting from Fourier series. And we say we already know this point. And then make omega to be very, very small to find out this line. That's how we use the way of thinking before. Now, let's reverse the thinking. So say that we already calculate our Fourier transform. We already know this line. And how we consider Fourier series, how we can get Fourier series from Fourier coefficient, how we can get Fourier series from already known Fourier transform. We just pick up values at some point. We get samples from Fourier transform. That's how we get Fourier series coefficient. Okay? So that's what is driven in here. So that's what this means. Let's assume that for one period, our on a periodic signal, which is not periodic signal, and a periodic signal, it's very confusing, but on a periodic signal, which is non-periodic signal x equals a periodic signal of x tilde for one period, right? They are one period, they are the same that we have used before. In those periods, to find AK, to find the Fourier series coefficient, we use 1 over t over one period of x tilde e jk omega 0 t, which is the definition of Fourier series coefficient. And we can switch for this one period, as these two are the same. We have learned in last lecture. We can switch this x tilde to x because they are the same only in this period. They are only in period, they are the same. And then from here, we can find something interesting. So in short, from the definition of AK, which is over a period, one period, x tilde e minus j omega 0 kt dt. We change for one period, which is those two are the same, we can easily change it to xt e minus j omega 0 kt dt. And remember our Fourier transform, how they looks like. They are minus infinite x t e minus j omega t dt. Keep in mind omega, not omega 0 k. So when you compare these two, what happens? In here, what is one more trick we try to have? As this xt is on a periodic signal, they are not periodic. That's a one-in-one signal. So even though we extend the range to minus infinity to infinity, there's no signal no smaller than s, larger than s plus t. So even though we extend them, does not matter. So we can have minus infinity xt e minus j omega 0 k t dt. So this is the Fourier series coefficient. This is Fourier transform. Let's find out the relationship between those two first using the equation. In the equation, what's the difference? Well, we made a form that there is a maybe only difference will be omega and omega 0, right? So, in short, this AK equals 1 over t, because in here, there's nothing in here, so 1 over t x j. If you put them, they will look like 1 over t minus infinity to infinity x e minus j omega t dt. It looks like this. Only difference will be here and here. So let's say we will have, just in case that omega equals omega 0k, right? So one you can see in here. Then when omega equals omega 0k, this one changed to from minus j omega 0 kt. They will change to like this, which is the same form, right? So equation-wise, we can consider Fourier series coefficient is equals 1 divided by the period multiplied by Fourier transform when omega equals omega 0k. What is the meaning of this one? What is the meaning of this one? Of course, this is a constant, like a scale factor, but another thing you can consider is this. Omega equals omega 0k. We have claimed that, before that we have claimed that we have Fourier transform, which is part of the function. And then Fourier series coefficient is getting a sample by spacing of omega 0, 1 omega 0, 2 omega 0, 3 omega 0, 4 omega 0, right? This one is the same meaning. We are taking omega, which is the general coordinate, at integer times omega 0. So we are taking a sample at omega 0, 0, omega 0, 2 omega 0, 3 omega 0, 4 omega 0, those kind of things. So we can consider them Fourier series coefficient as 1 divided by t, which is scale factor, and then Fourier transform at specific point, sampling by equally spaced omega 0. So that's why how we calculate. So this is another way we can calculate Fourier series coefficient. First, you calculate Fourier transform, and then change omega to omega 0k, scale by 1 divided by t. That's your Fourier series Fourier coefficient. If this is easier, use this equation. That's much easier. So meaning is, in frequency-wise, this is our the continuous case Fourier transform. Fourier series coefficient is sampling of each point. So that's what you say. Fourier series, the last word, Fourier series coefficient of x tilde are proportional to samples of Fourier transform of one period of x tilde. Because one period x tilde is equals to x, which is on a periodic signal, and then we can calculate Fourier series coefficient from it. One thing we have to make sure in here is Fourier series coefficient only exists in periodic signals, right? So Fourier transform can be workable both for Why there is, I think the person took my morning lecture. There is one insect disturbed the lecture. So another fly is flying over. Anyways, one thing you have to make sure is Fourier series is only valid for periodic signals. They are not valid for aperiodic signals. So this claim, this equation, only valid for periodic signals only, because in non-periodic signal, this AK does not exist. So keep in mind, if the signal is not periodic, don't use this equation. This is only valid for periodic signals. So, questions before we move on? And let's skip the convergence for a minute because that's not and go to page 11 example. Let's solve some of the problems. So let's find Fourier transform. Let's find Fourier transform for our x. Our x is given like that on top page in figure A, and they're given a form. It's like a rectangular signal. Make sure that this is not right. They are just one pulse. They are not a train of the pulse. Remember. In Fourier series, what we have learned before, we have utilized this pulse, the train of the pulse, because this is periodic signals. This is all periodic signal. However, in Fourier transform, we can use it both for periodic signal and aperiodic signal. Therefore, we have an example that this is not periodic signal, just one pulse. And they are one from here to here. Of course, this T1 is not period. Not period. That's just the timing of it. Let's calculate. Solution is quite simple. Let's write down over here E j omega equals minus infinity to infinity xt E minus j omega t dt. So let's use it. Xj omega equals minus infinity to infinity. Xt is what? Xt is only 1 when from minus t1 to t1. Other than that, they are 0. This is 1 over here. E minus j omega t dt. How do you calculate about this? E integration of E minus j omega t is what? Just have j omega over 1 right here. Right? And let's put t1, t2, minus t1. And then you will have minus j omega 1 E minus j omega t1 minus E plus j omega t1 because we put minus t1 here. And let's reverse the sign. Let's reverse the sign. And that's our answer. And this is what? E j omega t1 minus E minus j omega t1 is what? Using the Euler formula, right? Using the Euler formula, 2j sine omega t1. Is it right? Right? No. So using this one becomes like that. J will be removed. They will have a form that omega over 2, is it right? Sine omega t1. So calculation is quite straightforward. Doesn't need much effort. Much simpler than Fourier series, right? So we have to find the solution. And we have already learned about this. We briefly have a taste of this function as a sinc function. Sinc function has a form that sine x divided by x was form. So the variable falls to sine in numerator and doesn't have the variable comes as it is in the numerator. That's how we see it. So that's the answer. And let's draw it. When you draw it, so in time domain, the rectangular signal, which is minus t1 to t1 in time domain, they change to frequency domain. This one looks like what? Let's have omega, let's consider omega as a variable. This is sine wave basically, right? This is sine wave. So you can consider them as a sine wave. And this omega is 1 divided by omega. 1 divided by omega is what? They are decaying. Right? So we can consider them as sine times 1 over x. So the amplitude of sine is keep on decaying as our frequency going higher. So in short, they looks like a sine because they are oscillating, but they decay as frequency goes. So this is a sinc function. And one thing to note here is sinc function and rectangular has always have a pairing together. If the time is rectangular, frequency is sinc function. If frequency is rectangular, then time looks like a sinc function. Of course, they are not exactly same equations, slightly different number and scale, but they have very similar relationship. So, question, Piper. No question? Too simple? Too easy? All right. So we have this in frequency, okay, by far. So let's have reverse. Reverse means if our frequency is like this, our frequency is like this. Now it's frequency, not time. What happened to the time? We have to utilize our reverse Fourier transform. Reverse transform is given in here. 2 pi over 1 minus infinity to infinity, I think, x j omega e plus j omega t d omega. So this one changed time to frequency, that one changed frequency to time. So this is our frequency. This is our frequency. So they are 1 when omega is smaller than large omega. They are not. They are 0. They are 0 when omega is larger than large omega. That's how he claims. So to calculate that, use the second equation, which is xt equals 2 pi over 1 minus infinity to infinity. Likewise, they are only not 0 from minus w to w. Therefore, we can change this one to w to w. xj, which is 1 in this period, 1 e j omega t d omega. Make sure this is from frequency to time. And how do you calculate? Likewise, 2 pi over 1, we will have j omega over 1 e j omega t from minus omega to omega. And you keep on doing that, 2 pi over 1, j omega over 1, e j omega w minus e minus j omega w. 맞아요. Mistake. So they are doing over omega. So we have to put them in omega instead of t. I'm sorry. So j w t minus j w t. I'm sorry about that. So likewise, this one becomes what? 2j sine omega. I'm sorry, w t. Right. So this won't be cancelled. This won't be cancelled. So they have a form that so we are calculating, this is our variable, so t is constant, so jt should come out instead of omega. I'm sorry about that. So when you integrate this, omega is our variable, jt is our constant, so jt over 1 should come out. And we put w to omega in here to calculate that. Now this one becomes jt. So after that, 2 will cancel, j will be cancelled. So pi t over sine wt. That's what we can see in here. Make sure that this one is w, not omega, the frequency component. So the form is quite simple. So this is also zinc function. They have t at inside of sine in numerator, t at the denominator. So they also have form similar to like this. So this is sometimes called a duality. Dual are similar in two ways. From time to frequency, the impulse, the rectangular function changes into function. In frequency, the rectangular function in frequency changes into function in time domain. So they have a lot of similarity. Of course, the form is not exactly the same. If you see this one is omega 2 omega t1 divided by omega. So there is nothing in here. This one does not have 2, pi instead. So form is slightly different. But the difference is only the scale. Scale in y, t or omega, scale in y is different. But the basic, those shape will not change. So in our textbook, you can see problem 4.4, problem 4.5, they have both of them. So if you cannot understand, please take a look at it. Questions? So let's see one more time, define the zinc function. Zinc function, basic form of zinc function, this is a more common form. Sine pi theta, pi theta. If there is not exactly pi, you can take them out as a scale factor. And duality property of Fourier transform is, like what you can see in here, if the signal is rectangular signal in time domain, they change the zinc function. If the signal is rectangular signal in frequency domain, they change the zinc function in time domain. One thing to make sure is sometimes people define zinc as one function. If say zinc theta, typically they say pi theta divided by sine pi theta, something like this. If you want to say the second one right here, if you want to have a zinc function like that, you will have zinc T. First of all, you will have zinc T, which is given as, from here, sine pi T divided by pi T. You can do that. One thing you can do here is you can put it like that and say you have T will be changed because this is WT, this is pi T, so it does not match. To match it, we slightly modify this T. So let's change this T to pi divided by omega. I think it is reversed, should be reversed, right? Should be reversed. Pi over omega T as a new variable. So this pi T changed to, this WT changed to pi T using this. And to scale it, the bottom one also should be changed. The bottom one should be changed. To match it, we put a scale factor over here. So this form, you can leave it like that. There's no bad thing. This is not a wrong answer. This is the right answer. But sometimes you will confront the problem that they're given a zinc function like that. In here, you can consider them, okay, zinc function is defined in this way. So zinc, omega W divided by pi T is, will be sine pi theta is W by pi T divided by W by pi T. That's how it defines. So I'm not saying that you have to convert to zinc function. I'm not saying that. This is absolutely right. This is still absolutely right. However, some of the problems you may see zinc is given as problem itself. If zinc is problem itself, you can put them in this formula right here and then change it to this form and begin to solve the problem. But the important thing is that's not so important. Definition of zinc is not so super important. The really important thing is duality. We will have duality property for many times in Fourier transform and Laplace transform even. In short, going from time to frequency to time, they have a lot of similarities. That's what reason we call duality. One of the duality example is right here. You can see that from rectangular to zinc, zinc to rectangular to zinc, from time to frequency to time, they will be the same. Looks like a similar function. That's one of the duality you can see in here. There's another interesting you can see. I think I briefly introduced this one at the introduction, chapter 1. I mentioned that in frequency and time, they have a lot of similarities, but a lot of diverse property. For example, you can easily see from this following example. Can I erase? Any question before we move on? Nope. All right. So you can see from here. This is a frequency, right? This is frequency. So if you see in time domain, if the period become larger or smaller, say period becomes smaller, they will be more condensed. They will look like this. So when period becomes smaller, then they will be condensed, right? But if you plot them in frequency, of course, this is very conceptual explanation. You can see everywhere. We will go to the zinc function, more detail about it. So if you go to frequency, When this one goes down, then this one goes up. Their reverse property. So when this one is squeezing down, so in time domain, they looks like they become squeezing down, right? But this yellow signal has higher frequency than this white signal. So if you plot them in frequency domain, like say that this is part of the output of the low pass filter, the cutoff frequency of the white is here, then the cutoff frequency of this yellow will be here. So they will be extended in frequency domain. So this is one example you can see, we have already learned that in frequency domain and time domain, they have a lot of duality working similarly, but sometimes they work reversely. When in frequency looks like in time domain, they squeeze down, they are squeezing down. In frequency, they are spreading out. So let's have a real example on this using zinc function. Stoker, can you see this? I keep on using this side, but so using the equation we have learned before, let's have some examples. The last example we have is we have omega in frequency domain. This is rectangular signal in frequency domain. We change it to zinc function in time domain, which looks like that. If we change those W, if you change those W, make it small so that W2 is smaller than W1. Right? So W decreased. So they looks like they're squeezing down. If you decrease furthermore, omega 3 is smaller. In W1, in frequency domain, they looks like that, and then they're smaller. So they're squeezing down. This is very sensitive mic. I don't know why. What about that? If you plot the corresponding zinc function, when you decrease the omega, they are spreading out. So exactly reverse characteristic, meaning that it looks like in frequency domain omega, the bottom three, omega 1, omega 2, W1, W2, W3, they keep on getting smaller. The signal seems like squeezing down. However, in time domain, they looks like spreading out. So it's the same. It's exactly the same when you have rectangular in time and zinc in frequency. If you extend in time, the frequency will squeeze. That always happens. So not only that, the peak, this peak amplitude keep on decrease. That's one you can observe in typical these properties. So what I'm saying now here is for duality, you can see that duality means they are very similar from time to frequency, frequency to time. You can see that rectangular signal change to zinc change to rectangular. That's very popular. But what I emphasized before is they are not exactly the same signal. What it means here is, of course, the form is slightly different. Form was slightly different. There will be pi in frequency to time. There's no pi from time to frequency in zinc function. Not only that, the trend is slightly different. If you try to squeeze in frequency, they will spread in time. If you want to extend in frequency, they will squeeze in frequency in time. So they looks like reversely operating. Looks like that. Not only that, especially zinc function, the peak amplitude goes down. And you can see both things. Especially this one, you can often see in digital signal processing. So we have learned that zinc function and rectangular signal is always paired. However, where is our clock? I don't know. Someone hide it here. So they're always paired by far. So let's bring our claim one more time. We have learned that. Any questions by far? Questions? Nope. And we have learned that our Fourier series coefficient is, you can calculate Fourier transform, sample them by equally spaced omega and scale by t today. Let's see more deeply about this relationship. This one, I explained that this is only valid for a periodic signal. Periodic signals, because AK does not exist in non-periodic signal. Okay, so let's take more deeply. Let's take a look at more deeply about it. Both periodic and aperiodic signal functions can have Fourier transform. If its Fourier transform has a form that sigma 2 pi AK delta what's this omega should be omega, right? Omega minus k omega 0. If they say they have form like this, its Fourier transform is equal to Fourier series of periodic signals. What's the meaning of this one? So does not make sense a lot right now. Does not make sense a lot right now. But you can view them, you can consider them in the same way. So in here, we can consider them in a similar way. So in here, the later part, we consider them, they are sampling. We are taking samples at equally spaced omega 0, right? This one, the delta function works as similar function. Delta function is what? They are equally spaced. They are equally spaced by omega 0, right? And they are picking up samples at each spacing of omega 0. So this delta function works as what we have done before. So if you can represent x, j, omega like that, then they will same function. So in short, in Fourier transform, the last comment over here, Fourier transform of a periodic signal having Fourier series coefficient AK, they can consider to be a train of impulse, because as I said, they are taking samples in frequency domain at equally spaced omega 0. That was the same. That are harmonically related frequency, which is spacing of omega 0. The impulse of kth harmonic frequency at omega equals k omega 0, kth harmonic, they will be 2 pi ak. So what the meaning of this one is, first of all, this is still only valid for periodic signals. That's not valid for non-periodic signal. In periodic signal, we will have AK. If you want to have Fourier series coefficient, Fourier transform. The previous equation, we talk about the case that we already know Fourier transform. We sample them, scale them to find Fourier series coefficient. Now, what if the other way? We know Fourier series coefficient instead of Fourier transform. using Fourier series, let's transform it to Fourier transform. Transform is, so this one can be viewed as having an amplitude of 2 pi ak times the sequence of impulse. Remember, the sequence of the impulse is what? They are spaced by t0, having an amplitude over here. They may have this amplitude, different amplitude, which is given by this value, right? So we can view them as impulse or sequence of impulse, sum of it having an amplitude of 2 pi ak. Let's have an example. So let's keep it. Let's have an example. If xt is sine omega 0 t, we already have this example before. What is Fourier series coefficient of this one? What is Fourier series coefficient of this one? What is AK? Already forgot? Over period sine omega 0 t e minus j omega 0 kt dt. This is how we calculate. How we do it? We change this one to what? 2j over exponential j omega 0 t minus e minus j omega t, right? Everyone following? Right? And then over a period, we have t over 1, 2j over 1 over a period, e j omega t dt. Over a period, this is 0, right? I'm missing k, I'm sorry. It's k. This is a very common mistake. You will have it when you learn both Fourier series and Fourier transform. So in k, in here, of course, there's minus integration of exponential minus j omega 0 kt over here, of course. For this one is always 0 when e exponential value is not 0. No, I'm sorry. When k is not 0, then this one is always 0 because over a period, this is a periodic function. Over a period, they always go back to original value. Therefore, this is always 0 except one exception that k equals 0. Right? So while following this, we will figure out that our k is only not 0 when a is 1, k equals 1, k equals minus 1, which is 2j over 1 minus 2j over 1. That's what we calculate from Fourier series coefficient. Using this claim, we can find Fourier transform using this because we already know that, and they are only not 0 when k equals 1 and minus 1. So considering the impulse train, this impulse train is in frequency domain, not time domain, right? In frequency domain, when k equals 1, which is omega 0, and k equals minus 1, which is minus omega 0. Only those 2 points, they are not 0. And when omega 0, 2 pi ak is this amplitude. Ak is what? When k equals 1, is A1, 2, when k equals 1, it's omega 0, and which is 2 pi ak is what? 2 pi times 2j. So pi divided by j is this amplitude. So likewise, we just draw it, just giving you the polarity. So this is their Fourier transform. Likewise, when k equals minus 1, then 2 pi ak is simply given as 2 pi times minus 2j over 1. So pi minus j minus 1. So this is very similar to Fourier series. In Fourier series, let's go back to Fourier series for a minute. In Fourier series, we have claimed that, okay, they have a component in omega 0 of amplitude of this, in component of omega 0 minus omega 0 component like this. If you really draw it, and I once explained, okay, there will be eventually looks like this by omega 0 and minus omega 0. This is what I talk about in the beginning. So in short, we will have we try to find our Fourier transform. We try to have our Fourier transform. If the function is periodic function having Fourier series coefficient ak, we can consider them as impulse because we are taking samples having an amplitude of 2 pi ak. So if you can find ak, you can find Fourier transform. So this is one way. Another way we can find Fourier transform. Of course, you can use equation. Doesn't matter. You can use this equation to find this one. The solution will be the same. But I'm giving you another way you can find it an easier way. This is only valid for periodic signals. If it is not periodic signal, you cannot do that. What you can do is, if you already know their Fourier series coefficient, multiply them by 2 pi and find corresponding amplitude at each frequency. Each frequency you will given as 0, omega 0, 2 omega 0, plus minus, of course, plus minus 3 omega 0. So we're given as DC, fundamental frequency, and harmonics. Harmonics is what? The integer times the fundamental frequency, harmonics of the fundamental frequency. They are given as a sum of these frequencies. And of course, when you draw them, they will be given as, if this is not sine wave, for example, having amplitude at each k, in sine wave, we only have amplitude at, in sine wave, we only have amplitude at 1 and minus 1. In cosine wave, we already calculate that they will be given as 2 over 1, I think, right? So when you calculate Fourier transform, this amplitude will be pi. So we can think them when k equals 1 corresponding to omega 0 times 1, which is omega 0. And omega 0 amplitude of pi. When k equals minus 1 corresponding to omega equals, the frequency equals minus omega 0, minus 1 times omega 0 at here, the amplitude of pi, which is like that. So in cosine, in frequency domain, they will be represented like this, having an amplitude of pi. So this one saves you a lot of time if you already know the Fourier series coefficient, and only valid in periodic signals. One more thing I would like to emphasize here. Not only just to simplify your equation, there's one thing I would like to emphasize, especially important in many periodic signals. In periodic signals, in mechanical engineering, in electrical engineering, you have learned a lot of periodic signals because a lot of signals are repeating, right? So, if you are also, for example, in mechanical system, if you have a mass and the spring, if you keep on oscillate, what will be their frequency response? Let me rephrase my question. If the signal is periodic and have Fourier series coefficient, its frequency domain signal is discontinuous. Let me talk one more time. If the signal is periodic and have Fourier series coefficient AK, then its Fourier transform, which is their frequency component, is given as a sum, not integration, sum of impulses, spacing of omega. So they can be represented as a sum of impulse having different amplitude given by the amplitude is 2 pi ak, right? So there will be maybe DC plus minus omega 0 plus minus 2 omega 0 and go on. They cannot be continuous value in frequency domain. Of course, is this omega 0 infinity small, then they may be continuous. But just say the typical thing. In our periodic signal, which is omega 0 has some value, and say some periodic signal cannot have Fourier series, we have not learned it. However, assuming that we have a periodic signal having Fourier series coefficient, in frequency domain, its Fourier transform should be discontinuous, having a point spaced by omega 0, given as DC fundamental frequency omega 0 and harmonics of fundamental frequency. So if you see electrical engineering, if you see in mechanical engineering, a lot of them, they just draw in frequency domain, okay, they were given like this without many explanation. I think some of you take power electronics from me, see this one in my power electronics course. Because of this. In when we deal with many periodic signals in engineering world, they already have this one. And when they plot in frequency domain, because of this relationship, they have spaced powertrain, spaced train of impulse, which is DC fundamental harmonics. So they should be discrete. There's another important thing you can see from this equation. Just having simplify your calculation, but also it has some meaning like this. Okay, questions? Really? So these two give you a shortcut to calculate the Fourier transform for this. So this is another example you can find in our textbook. Say that, okay, we want to have Fourier series coefficient of a Fourier transform of this train. This is what? Periodic signal, which we already know our Fourier series coefficient, which is 1 divided by t. And then what happens? Each of them is a spacing of t. They will have omega 0. So you can think in this way. Okay, to draw here, draw like that, we need two things, amplitude and spacing. Right? If you know the spacing, if you know the amplitude, you can follow everything. First, spacing. Spacing is omega 0. In periodic signal, omega 0 is what? frequency is like that. So omega 0 will be 2 pi divided by t. Right? Omega 0 is fundamental frequency. Right? Fundamental frequency. Fundamental frequency is what? One reverse of the period times 2 pi to make omega. If you say fundamental frequency like this in hertz, they will be like this. So you can calculate from where? From the graph. The spacing of t. So omega 0 is already, we can draw it. We can calculate very easily. And what about the amplitude? We already know that they were given like 2 pi times ak. ak is what? From this equation of calculating Fourier series coefficient, we calculate ak already before, 1 divided by 1. This is our amplitude, right? So we know the spacing and we know the amplitude. So now, how we do it? We put the amplitude in this sigma delta omega times k omega 0, which is what? 2 pi times t. That's it. So much simplifies the load, calculation load. Also, you can find that they are spaced in fundamental frequency, second, third harmonic, fourth harmonic. In only periodic signals. Only periodic signals. So we have learned how only in periodic signal how we calculate that. So let's skim through the property of Fourier transform. First of all, so before we move to next chapter, next topic, questions. So keep in mind that in only periodic signal, a Fourier transform can do both periodic and non-periodic signal, but especially periodic signal, we have some advantage. We can use Fourier series, and Fourier series, between Fourier series and Fourier transform, in frequency-wise, in frequency domain, we can consider frequency, in frequency domain, if Fourier series coefficient is considered to be as sampling, and we can consider them as an impulse to find Fourier transform because they can be viewed as equally spaced. Of course, in drawing, it's not equally spaced, but actually it's equally spaced. Equally spaced have different amplitude. How you can find spacing from the fundamental frequency? How you can find amplitude? Just simply 2 pi times ak and find ak and make a train. That's it. And property. And property-wise, linearity. Linearity is valid for Fourier series and Fourier transform, both of them. So we have axt, byt. If you put them, there will be so at changed to xj omega corresponding, yt corresponding to yj omega. Let me rephrase a little bit. From here, Fourier transform is valid for both periodic and non-periodic signal. So this is in Fourier series. I emphasized that this relationship is only valid. In previous chapter, I emphasized that Fourier series is only valid for periodic signals. In here, doesn't matter. It can be periodic, cannot be periodic. Doesn't matter. Either of it. In here, linearity means if you have, this is the input. The corresponding is A plus B. That's the linearity. So you can calculate them individually and multiply. It doesn't matter. Second one, time shifting. So time shifting in Fourier transform is likewise when you have, you can see that in Fourier series also, right? When you have that, you'll have exponential something, right? Exponential minus j omega t0 x j omega. So the whole thing comes out as it is and multiply them in here. How you calculate? So if you say Fourier transform definition is minus infinity to infinite x t minus t0 exponential minus j omega 0 omega t. That's how you calculate in Fourier series. And let's put t minus t0 equals tau, some variable. And here omega minus t becomes minus j omega t equals tau plus t0 now, and dt equals d tau. Is it, Mark, can you understand? Are you following? All right. So d tau. So now this one becomes integration of minus infinity to infinity. This is the definition of the Fourier transform. So x tau e minus j omega tau times e minus j omega t0 d tau. So if you see this, they are definition of Fourier transform. So we can take this out, which is right here. Right? And conjugate. Conjugate means, I will leave this one for a minute so then we can compare later. Conjugate means if x has this relationship, what happened to x star? Conjugate. There will be x, this one, star minus j omega. That's how we defines it. So this is general case, this is general case, general case. If x is real, what happens? X equals x conjugate. Is it right? So using this relationship, we will find out that x minus j omega equals x star, I think j omega, is it right? So when x is real, using this relationship, you will find them both corresponding Fourier transform and then make them equal. You will have this relationship. Basically, this and this is the same. This way, so the result will be like this, right? Because x and x star is the same for real case, their transform should be same. The transform of x is xj omega, transform of x star is large x star minus j omega. So this is the actual initial value for your case. If you just change omega polarity, they will look like that. So it does not matter. This or this does not matter with the same meaning. For x is for the case x is real. If x is real and even, x is real and even, then there will be x minus j omega equals x j omega. See? Differential and integration. Actually, this is the very most important part, differential integration. You already know it. You already know it. If xt to differentiation, you automatically do that j omega, yeah, right? If you have integration, you automatically do that j omega over 1. Right? You already know it. But actually, if integration always have initial value. If initial value is 0, this is right. If initial value is not 0, actually there is something. Delta, right? So if initial value is not 0, then we have some constant afterward. We have learned by here because we assume that initial value is 0. If initial value is not 0, then we should consider that. Time, scaling, and frequency. When we scale in time, we scale them in time, then there will be so you can memorize using the duality thing. If you remember our rectangular, if this one expands in time domain, then this one will shrink down in frequency domain. Likewise, frequency domain, if you extend, this one changes. Also, its amplitude shrink down. I'm sorry, amplitude is going up. So when they shrink down, you are kind of squeezing in. If you're squeezing in, then amplitude will go up, right? If you extend it to the outside, they will spread out, but amplitude will go down. So you can think them, okay, if you extend it, then amplitude will go down and the frequency will shrink down. So you can think them in this way also.